The Star That Refused to Speak, August 2024. A telescope a million miles from Earth locks onto the brightest star in our night sky. Not a distant galaxy, not the edge of time, not the birth of the universe. A neighbor. For hours, the James Webb Space Telescope stares into a glare so intense it was never meant to confront. Its mirrors are tuned for whispers from the early cosmos, ancient infrared light stretched thin by billions of years. But this is not a whisper. This is Alpha Centauri A, a star so close its light barely weakens on its way to us, a star that floods detectors, a star that blinds. Webb blocks the core of that light with a coronagraph, an artificial eclipse. It waits. It collects photons. It subtracts patterns. It peels away glare, layer by layer. And then a faint point appears, small, steady, warm, just beyond the suppressed blaze of the star. It shouldn't be there. The signal is dim, almost fragile, 10,000 times fainter than Alpha Centauri A, but statistically strong, real enough to resist dismissal. For the first time in history, something may have been seen orbiting the nearest sun-like star to Earth. The team labels it cautiously, S1, not planet, not yet, just Source 1. 6 months later, Webb looks again. The star is still there. The glare is still there. S1 is not. Rewind. For decades, Alpha Centauri has been the most frustrating star in the sky. It doesn't hide at the edge of visibility. It doesn't flicker faintly among thousands of anonymous suns. It burns with confidence. On a clear night in the southern hemisphere, it's unmistakable, brilliant, steady, familiar. And it is close, just over 4 light-years away. In a galaxy 100,000 light-years across, that distance is almost intimate. If the Milky Way were scaled to the size of North America, Alpha Centauri would sit on the same city block. We have detected planets around stars hundreds of light-years away. Thousands of them. Some so distant, their light began its journey before electricity powered cities. But the star next door? Silence. That silence became a paradox. Because by the early 21st century, planet hunting had matured into precision science. Astronomers learned to detect the subtle gravitational wobble of a star tugged by an unseen companion. They measured dips in brightness when planets crossed in front of their host stars. They even captured direct images of massive, young worlds glowing in infrared light, entire catalogs filled with confirmed exoplanets, hot Jupiters hugging their stars, super-Earths in tight inner orbits, mini Neptunes wrapped in thick atmospheres. Systems unlike anything in our own solar neighborhood. Planets, it seemed, were common. Except here, the irony was almost poetic. We could survey distant solar systems across the galaxy, yet our closest sun-like neighbor revealed nothing. It was like mapping mountain ranges across an ocean while the hill outside your window remained lost in fog. Part of the problem lies in what Alpha Centauri actually is. It is not a single star. It is a family. 2 primary stars, Alpha Centauri A and Alpha Centauri B, circle each other in a slow gravitational dance that takes roughly 80 years to complete. Both resemble our Sun. Alpha Centauri A, in particular, is nearly a solar twin in size, temperature, and luminosity. At first glance, that similarity seems promising. If planets formed around our Sun, why not around its twin? But binary systems complicate everything. Imagine trying to build a delicate sandcastle while two shifting winds blow from different directions. The gravitational pull between Alpha Centauri A and B stirs the protoplanetary disk from which planets would form. Theoretical models once suggested that such systems might struggle to form stable inner planets at all. Then there is brightness. Alpha Centauri is the third brightest star in Earth's night sky. That brilliance may inspire poets. It frustrates astronomers. Telescopes designed to detect faint planetary signals operate like cameras tuned for candlelight. Point them at something as bright as Alpha Centauri, and they risk being overwhelmed. Finding a planet beside it is like trying to see a snowflake drifting across the face of a searchlight. The light doesn't just obscure, it floods the detector. It scatters. It diffracts into intricate patterns that masquerade as structure. And brightness is only one obstacle. Alpha Centauri moves. Because it is so close, its proper motion across our sky is one of the largest of any naked-eye star. Over time, its position shifts measurably against the distant background. For most purposes, that motion is subtle. For Webb, it is critical. A misalignment smaller than the width of a human hair seen from kilometers away could allow starlight to leak around the coronagraph mask, degrading the entire observation. Precision must be absolute, and there is still another complication. Perspective. Alpha Centauri lies against the crowded plain of the Milky Way. The background behind it teems with distant stars and faint galaxies. Any dim point of light detected nearby could belong to something far beyond the system. An unrelated object perfectly aligned along our line of sight. Distinguishing a true companion from cosmic coincidence requires ruthless analysis. So, Alpha Centauri remained quiet. Hints surfaced over the years. A possible Earth-mass planet around Alpha Centauri B was announced in 2012, only to be later questioned, likely noise buried in data. Hope rose, hope fell. Meanwhile, the exoplanet count elsewhere climbed into the thousands, and still, the nearest sun-like star system told us nothing. That silence carried emotional weight beyond science. For generations, Alpha Centauri has occupied a special place in imagination. It is the first destination in countless works of science fiction, the first harbor beyond the solar system. If humanity ever crosses interstellar space, Alpha Centauri is the logical first step. But what would we find there? A barren pair of stars orbiting each other in solitude? Or worlds? By the time the James Webb Space Telescope launched, the stakes felt different. Webb was not simply another observatory. It was the most powerful infrared telescope ever built. Positioned nearly 1 million miles from Earth at the second Lagrange point, it observes the universe in cold isolation, shielded from heat and glare. It was built to look backward in time, to study the first galaxies, to analyze the atmospheres of distant exoplanets transiting faint stars. It was optimized for the ancient and the faint, not the bright and the nearby. And yet, astronomers began to wonder. Planets do not only reflect light, they glow. When a planet orbits a star, it absorbs energy and re-emits it as heat. Even a cold world radiates faint infrared light, not visible to human eyes, but detectable by Webb's mid-infrared instrument, MIRI. At wavelengths around 15 micrometers, a mature planet with a temperature of 200 to 300 Kelvin emits measurable radiation. If a Saturn-like world orbited Alpha Centauri A at the right distance, Webb might detect its thermal signature, not reflected starlight, heat. The idea was bold. Pointing Webb at one of the brightest stars in the sky was risky. Its detectors are precious, irreplaceable. Overexposure is not a minor inconvenience, it is permanent damage. The observation required something unusual. Instead of locking directly onto Alpha Centauri A, Webb first aimed at a nearby reference star of manageable brightness. Once stabilized, it performed a carefully calculated blind offset, shifting its aim to place Alpha Centauri behind the coronagraph without ever centering it directly. Every variable had to be accounted for. Proper motion. Parallax from Earth's orbit. Orbital motion between A and B. Nothing could be assumed static. And then there was Alpha Centauri B itself. Even if A were perfectly suppressed, B's light could scatter across the detector, creating complex halos and diffraction spikes. Months of simulations preceded the first attempt. Engineers modeled light patterns, tested subtraction algorithms, rehearsed the blind offset in software. Webb, designed to explore galaxies at the edge of time, was being pushed into new territory. There is something poetic about that. A telescope built to see the first light of the universe now turning inward, toward the star next door. Because sometimes the greatest discoveries are not waiting at the edge of the map. Sometimes they are hidden in the glare of something familiar. In August 2024, Webb stared. Hours passed. And infrared photons streamed in, tiny packets of energy that had traveled 4 years through interstellar space. The raw images looked chaotic. Diffraction spikes radiated outward. Scattered light streaked across the field. Noise overlapped with structure. To the untrained eye, it was abstract art. But astronomy is not about what the eye sees first. It is about what remains after everything else is removed. Reference star differential imaging stripped away instrument behavior. Algorithms identified correlated noise. Patterns were subtracted, refined, recalculated. Layer by layer, the glare thinned, and then a faint point-like source. Stable, distinct. Approximately 1.5 arcseconds from Alpha Centauri A. Not dramatic, not blazing, just a small, steady warmth in the infrared. Well, Webb had done what many believed nearly impossible. It had looked into the glare of the nearest sun-like star and found something beside it. Whether that something was a planet would take months to determine, but one fact was undeniable. Alpha Centauri was no longer silent. And the quiet that followed would become far more unsettling than the silence that came before. The planet that shouldn't disappear. The first rule of astronomy is simple. Do not trust the first image. When S1 appeared in August 2024, no one celebrated. Not yet. The data were promising, strong even. The signal cleared the statistical threshold astronomers demand before taking something seriously. 5 sigma. In plain terms, the probability that this was random noise was extraordinarily small. But small is not 0. And Alpha Centauri had fooled scientists before. So the team did what science requires. They tried to destroy their own discovery. First question. Background object. Alpha Centauri sits against the dense plane of the Milky Way. Behind it lies a crowded field of distant stars and faint galaxies. A tiny unresolved galaxy, perfectly aligned along our line of sight, could mimic a planetary signal. The team checked archival surveys. Nothing known occupied that position. They examined older images taken at different wavelengths. If a background galaxy were responsible, some trace should appear elsewhere in the spectrum. There was nothing. Second possibility. Foreground contamination. Could S1 have been an asteroid drifting through our own solar system during the observation? As solar system bodies move relative to background stars, over hours, that motion becomes detectable. S1 did not move. Across the full observation window, it remained fixed relative to Alpha Centauri A. Third possibility, instrumental artifact. Coronagraphs suppress starlight, but they do not eliminate it. Diffraction patterns create speckles, tiny bright spots that can masquerade as companions. Under certain conditions, these speckles persist long enough to look convincing, so the team injected artificial planet signals into the raw data. Synthetic companions with known brightness and position were added, then processed through the same reduction pipeline. Real sources behave differently from artifacts in subtle statistical ways. S1 matched the behavior of the injected planets. It did not behave like noise. And every obvious explanation failed. Its separation from Alpha Centauri A, about 1.5 arcseconds, translated to roughly 2 astronomical units, twice the Earth-Sun distance. That region lies near the outer edge of the star's habitable zone. Its infrared brightness implied a temperature between 220 and 250 Kelvin, around minus 50 degrees Celsius. Cold, but not frozen in deep space. Modeling suggested a mass comparable to Saturn, perhaps slightly heavier, large enough to hold a thick hydrogen-helium envelope, too small to ignite fusion. If confirmed, this would not be a hot Jupiter skimming its star. Not a young world glowing from formation heat. It would be something rarer, a mature, billion-year-old gas giant orbiting a sun-like star, and not just any sun-like star, the nearest one. If S1 were real, it would instantly become the closest directly imaged exoplanet candidate in history. That fact alone demanded caution. Because extraordinary proximity demands extraordinary proof, the only way forward was motion. Planets move. They do not hover frozen beside their stars. They trace arcs governed by gravity. Kepler's laws allow no exceptions. If S1 orbited Alpha Centauri A, it would shift position over time in a predictable way. The team ran orbital simulations. Short-period orbits would move quickly, longer ones more slowly. Circular paths would produce gentle arcs. Eccentric ones would swing dramatically between wide and tight separations. Almost every plausible solution predicted the same thing. S1 should still be visible in early 2025, maybe shifted slightly, but there. Follow-up observations were scheduled for February 2025. There was quiet confidence. Webb had performed flawlessly in August. The blind offset worked. The coronagraph suppression was stable. The data reduction pipeline had proven itself. If a Saturn mass world sat where models predicted, Webb would see it again. February arrived. Webb stared once more into the glare. Hours of exposure. Infrared photons streaming across 4 light-years. Data flowing back from L2 to Earth. Processing began immediately. The team subtracted reference patterns, modeled diffraction, applied principal component analysis, searched the predicted region. Nothing. No faint dot. No residual warmth. No statistically significant source. They widened the search area. Perhaps the planet had moved more than expected. Orbital motion can change both angle and separation. Still nothing. They reprocessed the data from scratch. Different noise thresholds. Alternative subtraction methods. Independent teams working blind to avoid bias. The result did not change. S1 was gone. There is a particular silence that follows a null result. Not disappointment, confusion. Because the telescope had performed perfectly. Sensitivity matched or exceeded the August observation. If a Saturn mass planet remained in roughly the same region, Webb should have detected it. But the frame showed empty space. April 2025 offered another opportunity. Perhaps February had caught the planet at an unfortunate orbital phase, too close to the star, partially buried in residual glare. A few months might shift it outward again. April's data arrived. The same reduction steps, the same scrutiny. Again, nothing. The object that had appeared with high statistical confidence in August 2024 did not show itself in February or April 2025. The simplest explanation hovered uncomfortably close. Maybe S1 had never been real. Even 5 sigma detections can betray us. Rare fluctuations happen. Instruments produce artifacts that survive multiple tests before revealing themselves as illusions. Astronomy has a long memory of such moments. Signals celebrated, then retracted. But something about SS1 resisted that narrative. The August detection had behaved consistently across independent subsets of data. It did not flicker like a speckle. It did not smear like a diffraction artifact. When it matched the expected signature of a genuine point source under Webb's optics. And then there was the deeper truth. Planets do not vanish. Or do they? The answer lay not in the telescope, but in geometry. A coronagraph does not see equally in all directions. Its sensitivity varies across the field of view. Diffraction around the mask creates regions of optimal contrast and regions effectively blind. Imagine shining a flashlight through a small opening. The beam is not uniform. Some angles are brighter. Others are streaked with interference patterns. A tiny object drifting through that beam might appear brilliant in one position and invisible in another, without changing at all. If S1 followed a highly eccentric orbit, its distance from Alpha Centauri A would vary dramatically. So at Apastron, the farthest point, it would sit at maximum separation, easier to detect, clear of the worst glare. As it moved toward Periastron, it would draw closer to the star, entering regions where residual starlight overwhelms faint planetary heat. In that case, disappearance would not mean destruction. It would mean concealment. Orbital simulations began again, this time with a different question. Not, is it real? But under what conditions would it appear in August and vanish in February? Thousands of orbital configurations were generated. Eccentricities varied, inclinations tilted, periods adjusted. The results were unsettling. More than half of dynamically stable orbital solutions produced exactly that pattern. Visible in August. Hidden by early 2025. In many scenarios, S1 would have been near Apastron during the August observation, far enough from the star to emerge from glare. By February and April, it would have moved inward along an elliptical path, crossing into regions where Webb's contrast performance drops below detection threshold. The planet would still be there. Webb simply could not see it. Statistically speaking, non-detection in early 2025 was more likely than continued visibility for many plausible orbits. The mystery had not collapsed. It had deepened. Then another thread resurfaced. In 2019, years before Webb's observation, astronomers using the Very Large Telescope in Chile reported a faint tentative signal near Alpha Centauri A. That candidate, labeled C1, was never confirmed. Though ground-based observations suffer from atmospheric turbulence that can mimic planetary signals. C1 faded into uncertainty. But its reported position lay closer to the star than S1's August 2024 location. What if they were the same object? If a single planet followed an eccentric orbit, it could have appeared closer in 2019, farther out in 2024, and then slipped inward again in 2025. Simulations incorporating both positions revealed something remarkable. A family of orbital solutions satisfied both hints. Eccentricity near 0.4. Orbital period between 2 and 3 Earth years. Significant inclination relative to the binary plane. Such an orbit would be unlike any major planet in our solar system. More elongated than Earth's nearly circular path. More dynamic. It would also explain the vanishing act. At certain phases, S1 would sit in the coronagraph's sweet spot, where contrast is optimal. Months later, it would drift into a zone dominated by diffraction and residual glare, becoming effectively invisible. The February and April observations did not kill the planet hypothesis. They made it stranger. Because now, confirmation required patience. If the simulations were correct, S1 would swing outward again, returning to a favorable separation in mid to late 2026. Another window, another chance. If Webb observes Alpha Centauri during that predicted phase and finds S1 near the expected position, the case becomes overwhelming. A consistent gravitational arc across multiple years would eliminate nearly all alternative explanations. If it fails to reappear, the mystery grows darker. Either way, something profound has already happened. For the first time, we may have glimpsed a mature world orbiting the nearest sun-like star. And for the first time, that world may have slipped from view. Not because it vanished, but because physics briefly hid it from us. Planets orbit. Stars shine. Geometry decides what we see. And somewhere, 4 light-years away, Alpha Centauri continues its quiet dance, indifferent to the debate unfolding on a small blue planet that has just begun to see clearly. If S1 is real, let's assume for a moment that S1 is real. Not a fluctuation, not a background illusion, not a statistical ghost hiding in the glare, but a planet, a world orbiting Alpha Centauri A, the nearest sun-like star to Earth. What kind of world would that be? The infrared signature gives us the first clue. At roughly 15 micrometers, S1 radiated heat consistent with a temperature between 220 and 250 Kelvin, around minus 50 degrees Celsius, colder than Antarctica's interior, warmer than Saturn's upper clouds. Not a blazing hot Jupiter, not a newborn world glowing from leftover formation heat. Something older, cooler, settled. The brightness suggests a mass comparable to Saturn, perhaps slightly larger, somewhere between 80 and 150 Earth masses, large enough to gather and hold a thick hydrogen-helium envelope, too small to ignite fusion, a true planet, and its orbit is what makes it extraordinary. Alpha Centauri. A shines slightly brighter than our Sun. That shifts its habitable zone outward, the region where liquid water could exist on a rocky surface. S1's estimated orbit, swinging between roughly 1 and 2 astronomical units, places it near or within that temperate band. S1 itself would not be habitable. Gas giants do not offer surfaces to stand on. Beneath their cloud tops, pressure increases relentlessly. Hydrogen compresses into exotic states. What looks solid from space is only atmosphere deepening into extremes. But giant planets rarely travel alone. Jupiter has more than 90 moons. Saturn has even more. Some are small and irregular. Others are worlds in their own right. Titan carries a thick atmosphere and liquid lakes, though made of methane instead of water. Europa and Enceladus conceal global oceans beneath icy crusts. These moons are not static rocks. They are active, evolving environments. Now imagine such moons orbiting S1, but warmed not only by tidal forces and internal heating, also by the steady light of a sun-like star. A large moon orbiting within Alpha Centauri A's temperate zone could receive enough stellar energy to maintain liquid water on its surface, if its atmosphere were thick enough. Instead of a frozen ocean trapped under ice, water might flow openly. Clouds might gather, rain might fall, and in its sky, 2 suns would hang. Alpha Centauri A. Bright, golden, familiar in color and intensity. And farther away, Alpha Centauri B. Smaller in appearance, but still luminous. Over decades, as the binary pair completes its slow 80-year dance, B would shift position, casting subtle secondary shadows. The sky would not be static, it would evolve. This is no longer abstract science fiction. It is physically plausible. If S1 exists, and if it hosts substantial moons, the nearest potentially temperate environment beyond our solar system may already lie just 4 light-years away. But S1's possible orbit adds complexity. Simulations suggest an eccentricity near 0.4, far more elongated than Earth's nearly circular path. That means S1 does not maintain a constant distance from its star. At closest approach, it would receive substantially more radiation. At farthest separation, significantly less. For any moon orbiting it, climate would not follow simple seasonal cycles. Instead, multi-year oscillations could dominate. Ice caps might expand and retreat over orbital timescales. Atmospheric chemistry might pulse in rhythm with gravitational dynamics. Weather patterns could be extreme. We have never directly observed such a mature and temperate gas giant before. Every directly imaged exoplanet discovered prior to this has been young and distant from its star, glowing brightly but offering little insight into long-term planetary stability around sun-like stars. S1, if confirmed, would change that. It would become the first directly imaged billion-year-old gas giant orbiting within the temperate region of a solar twin. And it would orbit the closest solar twin to Earth. That proximity matters. Not emotionally. Physically. 4 light-years is not a trivial distance, but it is reachable in principle. Concepts like laser-driven light sails, fusion propulsion, and beamed energy systems are theoretical today. But over centuries, perhaps sooner, interstellar travel to Alpha Centauri remains humanity's most realistic first destination. If S1 is real, then that destination contains a world. A system once thought barren may be populated. There is another implication, quieter but equally important. Binary star systems are common in the galaxy. Nearly half of Sun-like stars exist in binaries or multiple systems. For years, some models suggested that such environments might inhibit stable planet formation in inner regions. Gravitational perturbations from a stellar companion could disrupt protoplanetary disks, scattering material before planets fully assemble. But if S1 occupies exactly the region theoretical models predicted as marginally stable and survives there in an eccentric orbit, then planet formation in binary systems may be more resilient than once assumed. That changes statistics. If binary systems can form and maintain planets in stable temperate zones, then the number of potentially habitable environments in the galaxy increases dramatically. Alpha Centauri would no longer be an exception. It would be evidence. But before rewriting textbooks, patience is required. Because everything depends on 2026. If S1 returns to visibility during its predicted orbital phase, emerging once again from the glare at the expected separation, then the case becomes overwhelming. A consistent gravitational trajectory across multiple years would rule out background coincidence. It would rule out transient artifacts. It would transform a candidate into confirmation. And if it does not return, then the puzzle deepens. Perhaps the orbit is even more complex than modeled. Perhaps additional unseen bodies perturb its motion. Well, perhaps our understanding of coronagraph performance at extreme contrast requires refinement. Or perhaps, despite every test, S1 was an illusion. Science is built to survive disappointment. But this time, something feels different. Because the disappearance itself fits too cleanly within orbital geometry. Because more than half of stable solutions predict exactly what happened. Because Alpha Centauri has been silent for too long, and now the silence has shape. In mid to late 2026, Webb may look again. It will perform the blind offset. It will suppress the stellar core. It will wait for faint infrared photons to accumulate. If S1 is there, it will appear not as a surprise, but as a traveler returning to a predictable waypoint in its orbit, a world stepping briefly into visibility before continuing its silent revolution. And if that happens, history will shift quietly. Not with a headline announcing life found, not with a dramatic revelation, but with something subtler. the nearest sun-like star would no longer be an empty lighthouse. It would be a planetary system. 4 light-years away, Alpha Centauri continues its slow, indifferent dance. Its twin stars orbit each other. If S1 exists, it traces its elongated path through invisible gravitational lines. Perhaps moons circle it. Perhaps weather systems churn in alien skies beneath 2 suns. And here, on Earth, we wait. Because sometimes discovery is not about distance. It is about persistence. Alpha Centauri refused to speak for nearly a century. Now, for the first time, it may have whispered, and in 2026, we will listen again.